The aim of this presentation is to introduce the concept of electric potential. Now, it's important for me to just mention right up at the start here that electric potential, so potential, is not the same as potential energy. The two quantities are related, but they're not the same. So we're going to look at electric potential energy first and introduce that by talking about gravitational potential energy. We're going to talk about electric potential and how that's different to potential energy. We're going to look at equipotential surfaces and finally talk a little bit about a uniform electric field and the special types of calculations that we can do with those. When an object, I'm really sorry for objectifying this guy here, when he falls in a gravitational field, the gravitational field applies a force on that object over a distance, and I've just noted here that a force over a distance means work has been done. So you get a change in potential energy. It goes from a high gravitational potential energy to a low gravitational potential energy. So what happens when I push that object back up again? So he's fallen from here. I'm just going to change the colour of my pen. He's fallen down and got a lower gravitational potential energy. When I apply a force on that guy and push him all the way back up again, I'm applying a force over a distance and the gravitational potential energy is increasing again. I'll draw him back up here. Unfortunately, my class are already familiar with my stick figure, which kind of looks like a starfish with some kind of tumour on the end of one of its legs there. But anyway, that is my stick figure. So I'm actually doing work on that object, so its potential energy will change. It will increase. So whenever work is done on an object by a gravitational field or against a gravitational field, the object's potential energy will change. And this applies to an electric field. I've drawn here an analogous situation with a positive test charge up here, and it obviously will be attracted to a negatively charged body down here. But the same ideas apply even when the test charge is being repelled. I'm just not going to talk about that situation specifically. So the field is doing work on the charge as it's attracted to it. So the field is actually pulling that down. It's doing work on the charge. So its potential energy will change. It will decrease. As I move, so it's gone down here. As I move the charge up again, pushing it all the way away, I have to do work on that charge. I have to apply force over distance, and it ends up back there. So its potential energy will increase. So the main point to take away here is that a charged particle which is moving with or against an electric field will have a change in electrical potential energy. So just an extra note here that if this charged body down here was positive, so if we made them all positive, I won't do them all here, then the test charge would just have a higher potential energy closer to here because it would have the potential to go really fast as it got repelled, as it goes whizzing out that way. So everything would be turned around in sign. So now we're going to talk about, we have been talking about potential energy, and before we move on to potential, it just wouldn't be physics unless we rewrote those words into an equation. So I'll just do that quickly for potential energy. So potential energy, and the potential energy we're talking about is obviously electrical potential energy, has a different symbol to what you're used to. Of course it does. Of course it has a different symbol. We give it the symbol large U. Wouldn't expect anything different, would you? We'll call it U, and it's measured in joules. So the change in electrical potential energy, so the change in U is just the work done. It's the change in electrical potential energy is the work done on the object. Now, we can define a kind of an absolute potential energy at some point in space, and we'll call that U just on its own. And we can calculate by saying it's the work done by bringing that object from a very, very, very long way away to that point in space. So this is the potential energy between points A and B, and it's the work done to bring it from A to B. And let's call this point A down here, and we're bringing it to point B here. So the electrical potential energy at point A is the work done in bringing it to point A from a long, long way away. So finally we're going to get on to talking about electric potential, and we're going to do something that's a bit odd. We're going to start talking about, that by talking about potential difference, because I think it's just an easier step to make conceptually. Potential difference is related to potential energy. Potential difference between 2 points, so between A and B, is a measure of the change of potential energy per unit charge that charge, or this positive test charge, would experience if it was moved between those 2 points. So it's the work done in moving that charge from point A to B. The key difference here is this per unit charge. This means that instead of us talking about the change in potential energy of the whole charge, we're talking about the potential energy for each coulomb of charge. And if we went back to the analogy with gravitation, it would be like saying the change in gravitational potential is equal to the change in gravitational potential energy per kilogram of mass of that object. And so we're going to write an equation for that, of course. So the change in potential, or the potential difference, we're going to call delta V, so the change in V. And we're going to see in a minute that, look, this V here is also called voltage, so the potential difference is also called voltage. And that is equal to the work done divided by the charge, so it's the unit, divided by the charge, so it's per unit charge. Work, of course, is just the change in potential energy, and it's measured in joules. Charge is measured in coulombs, and so we can work out that potential difference, or the voltage, is measured in joules per coulomb. Or, what unit do you know for voltage? Yep, it's volts, and it's the same quantity. So I'll just highlight that because that's an important equation. There we go. So that voltage might look familiar to you, and this is just where the voltage comes from. The potential of a point anywhere in the electric field, so we're looking at potential now, not potential difference, is just the work done per unit charge moving a positive test charge to that point, so moving this charge to this point A from a very, very long way away. And that's just written in words there. And again, the equation is just a simpler version of what we had before. I'll just change my pen back to black. It is voltage, for the potential at a point A is the work done bringing it to A per unit charge. It's worth pointing out here that it's worth pointing out that the change in potential energy of this charge between 2 points, so A and B, is independent of the path the charge takes to get from A to B. So we've just drawn a straight line here. But what we could do is take a more meandering path. We could go out a nice little stroll, and then, oh, forgot something, need to go back to collect it, and then we might take a pause, and oh, we're going to do, going on a roller coaster this afternoon, and we get to point B. And that's because when we're moving the charge one way, So as we're going from A to B, the work done by the field is negative, whereas whether I do work on the charge moving it back the other way against the field, the work on the charge is positive. So things kind of cancel out if you go backwards and forwards. And you only are doing work on the charge if it's moving in changing the electric field strength as you're moving it. And you know this in the analogy of gravitational potential energy between, if you move an object from the ground floor to the third floor, it's independent, the change in potential energy is independent of how you move that object, whether you threw it up or whether you carried it up the stairs. So before I give you another experience with my fabulous drawing skills, I'm going to talk about now equipotential. And just as an introduction to that, these are basically the same as contour lines. So the lines of equal height on a map, so contour lines on a map that we see here. So this is our island, and then if we look at it from the top, you can draw the lines of equal height, or the isobars, or the lines of equal pressure on the weather map down in the bottom corner here. Right, so here's equipotential explained. Here is a spherical charged body. Let's say it's positive for now. What would my electric field look like around this body? Well, to figure that out, all you need to do is ask yourself, what direction would a little positive test charge do if it were put around that field? And it would be repelled, wouldn't it? So it would be going out that way. So wherever you put that positive test charge, it will be heading away. It will be being repelled from that body. So notice that close to the sphere, just going to draw these a bit better. Close to the sphere, the field lines are really close together, which means the field is strong, close into the sphere. And as we move away from the sphere, the field lines get further and further apart as the field becomes weaker. So at all points on some spherical shell around this central sphere have the same field strength. And if they have the same field strength, the amount of work it would do to get a charge to that point would be the same. So they have the same potential. So we can draw lines of equipotential around this spherical object. And in 3 dimensions it would be spheres around rather than circles, so there could be surfaces of equipotential. So here's our surfaces of equipotential. There we go. Not bad, a little egg-shaped, but they should be spheres around the sphere. So these are surfaces of equipotential. You'll notice, you might be able to see, that no matter where you look, should be the case, that the surfaces or lines of equipotential are always at right angles to the electrical field lines. Doesn't matter where you look, they always should be at right angles. So let's move on to a special case, which is the potential difference. Oh, sorry, here's an example of just a more complicated situation, and these dotted lines are the lines of equipotential. So you could draw your field lines, work out how they look around two charges, positive or negative, and you can do all sorts of more complicated things if you felt the need. And you could draw at right angles to that the lines or surfaces of equal potential. Yes, so here's our special case. We're going to talk about the potential difference across a wire. So here's my wire, long straight wire. I'm going to call this end negative, I'm going to make this end positive. So, which way does the electric field point in this wire? You need to think about what a positive test charge would do, and that's right, within this wire the positive test charge would be going up, so the electric field is going that direction. If we consider what the electrons are doing in here, just write the little symbol for an electron there, what is that, which way is that electron going to travel in this electric field? Well, it's going to go the opposite direction because it's a negatively charged object, so the electron is going to go that way. Because we've got an electric field here and we've got a charge, considering this charge moving the electric field, we can talk about there being a potential difference between one end of the wire and the other. So what will happen to the potential energy of the electron as it moves from one end of the wire to the other? Well, it's going to change. So for the electron, if it's coming from the negative end up here and going all the way down, as we drew before, to the positive end down here, it's going to have a change in its electrical potential energy. It's going to have a lot of electrical potential energy up here, and it's going to lose electrical potential energy as it's going down there. And where's that energy going? It can't just disappear. It actually goes into the kinetic energy of the electron, which results in the heating up of the wire. So how about we draw it like this? Instead of a long straight wire like that, we draw the two ends of the wire, negative and positive there, and we bend the wire into a big loop. Is that looking familiar to you? Yep, this is just about the most basic circuit you can get. What provides the electric field in this circuit? Obviously, electric field is going from positive to negative inside that wire. It's the positive and negative terminals of the battery. So the battery will be up here. Means there's a potential difference between the two ends of the wire. Means that electrons will be repelled from the positive end. Just draw that in there. Whoops, I've done that wrong. The electrons will be going that way. And they'll be attracted to the positive end, and in moving across that potential difference, they'll convert some of their electrical potential energy, which they had a lot of over here at the negative terminal. So over here at the negative terminal, they had a lot of potential energy. It's almost like they're falling down the electric potential and getting rid of that energy, or converting that energy into kinetic energy as they go through the circuit. And this concept we're going to use when we're talking about electric circuits later. Just before we wrap up, I'm going to end with a review with a little analogy between gravitational fields and electric fields in the special case of, let's go back to black, a uniform electric, let's just say uniform fields because we're talking about both uniform fields. And a uniform field is just where the field is constant everywhere in that space. So we're going to start over here with the situation of dropping a ball, just to save you the trauma of seeing me draw one of my stick fingers again. So we know that in real life the gravitational field of the Earth changes as you get higher because you get further away from the Earth, so the field lines will be further apart and as your gravitational field gets weaker. But we're going to say that in this particular point in space that the field is approximately constant between the ground and some height, which we'll call h above the ground. So here's our ground down here. So the analogy of that is in a circuit, if you have two plates, two parallel plates, and they're connected up to the rest of the circuit here and here. And we won't worry about it for now, but let's say that we've got a positive charged plate up here and a negatively charged plate down here. So this creates a uniform field between the plates, and if I wanted to, and you've seen this before, you'd just be drawing your lines in the direction, field lines in the direction that a positive charge would move, so they would all be going down like that, and they would be the same distance apart. But for now, I'm just going to get rid of all of those because you know that already. So just going to talk about 4 quantities to compare them between gravitational fields and electric fields. So the first one is force. And this is just a review. If we look at force in a gravitational field, force is just the mass times a measure of that field, which is the gravitational acceleration. Over here, the force is the charge that's moving. Let's say we've got a charge moving here, and let's make that, just move that over here. Here's our charge, and it's positive. And this distance we're going to call, between those two plates, it's going to be called D. So the charge, the force is just the charge times the electric field strength in that, and it's uniform. So in here, with the analogy is that we're talking about a mass in the gravitational field, our charge in the electric field, and each one of them you just multiply by a measure of the strength of the field. So here it's called E, and here a measure of the strength of the field here is the gravitational acceleration. So the next quantity is the work done in each as you move something. So the work done is just the force times the distance. If I lifted that ball up from the ground to a height h above there, it would be the force mg times h. If I moved this charge from down here in the negative plate and I moved it a distance d across there, then it would just be the work, still the same, force times distance equals E Q D. Of course, we could talk about a smaller distance in there, and we could work out the work for that smaller distance. The next one that I'm going to talk about, I'm going to write it out in shorthand here, change in potential energy. So the change in potential energy, I'll call it EP, here is equal to the work, which is mgh, to lift that ball up. And over here, the work, the change in potential energy here, delta U, is just the work again, which is the same as what we have above EQD. So finally, the change in potential. Over here, the change in potential, so delta V, or the voltage, is the same as the work, or the change in potential energy, divided by the charge. So if we look at that, it's E, Q, D on Q, which equals E, D. So that is the change in potential across two parallel plates which are a distance d apart. Over here, we don't usually talk about the potential, the change in potential for a gravitational field, but we can do the same thing. It would be, again, the change in potential energy, or the work done, divided by the mass, the object that we're concerned about, and it would be the GH. We just divide through the potential energy by M. So there's our little analogy. To summarize, the electric potential energy of a charge changes if we do work on it in an electric field. So we can either do work on that charge to move it, or the field itself can do the work, and that will determine what sign it is, but the change in potential energy is the work done. The electric potential difference between 2 points in an electric field and somewhere in space is the work done per unit charge in moving, say, a positive test charge between those 2 points. And finally, just a little reminder there that the lines of equipotential, so the lines of equal potential, are always perpendicular to electric field lines. Thank you for staying with me, and we'll work through some problems together.